Seriously, mind-bending physics.
Always ready for a trip down the quantum rabbit hole.
Today we're taking on quantum spin and entanglement. Two concepts that might sound like something straight out of sci-fi.
But they're not science fiction, they're very real. And they have some pretty wild implications for the universe as we know it.
So let's start with the basics. When you hear the word spin, you might think of like a spinning top, right? But it turns out it's not quite that simple in the quantum world.
Not even close. Yeah, these particles aren't actually spinning like little balls. Instead, they have something called intrinsic angular momentum.
Intrinsic angular momentum. Sounds complicated.
It is a mouthful, but think of it like this. It's a fundamental property of particles, just like electric charge. But instead of attracting or repelling other particles, spin determines how particles behave when you rotate them.
So it's like an internal compass that tells them how to orient themselves.
Exactly. It's like a built-in sense of direction.
Okay, that kind of makes sense. But here's where things get really weird. Just like charge comes in discrete units, so does spin. It's quantized, meaning it can only take on specific values.
It's like climbing a staircase. You can only step on the stairs, not in between.
So no half steps allowed in the quantum world.
Nope. And this has some pretty big consequences. For example, electrons, the tiny particles that orbit an atom's nucleus, they have a spin of plus or minus 1/2 h bar.
Okay, h bar, just a tiny bit of physics jargon there.
Cool.
It's the reduced Planck constant, a super tiny number. But the point is, spin is fundamentally different from anything we experience in our everyday lives. It's like a whole new set of rules.
Exactly. And these rules have a profound impact on how particles behave and interact. It determines whether a particle is a fermion or a boson.
Fermions and bosons. Sounds like something from Star Wars.
Huh, yeah. But in reality, they're just two fundamental types of particles. And the difference between them comes down to their spin.
So how do we tell them apart?
Well, fermions, like electrons, have half-integer spin. And they obey a very important rule called the Pauli exclusion principle.
Okay, so what does that mean?
It means no two fermions can occupy the same quantum state. It's like a cosmic game of musical chairs. But there's only one chair for each fermion with a specific set of quantum numbers.
So they're all vying for their own unique spot. But why is that so important?
Because it's the reason why atoms have structure, and why matter doesn't just collapse in on itself.
Whoa, hold on. So this non-spinning spin is actually the reason why atoms are stable.
Yep. If electrons didn't follow the Pauli exclusion principle, they'd all just cram into the lowest energy level around the nucleus, and atoms would implode.
So we don't have the diversity of elements, the complexity of molecules, or, well, us.
Exactly. All thanks to this quirky little property called spin.
Okay, so spin is clearly a big deal. But how does entanglement fit into all of this?
Well, that's where things get even weirder. Entanglement is like a spooky connection between two particles where they become linked in a way that defies our everyday intuition.
Spooky. You mean like ghosts and goblins?
Huh, not quite. But it did spook Einstein, who famously called it spooky action at a distance.
All right, I'm intrigued. So what's so spooky about it?
Imagine you have two particles, let's say electrons, and they're entangled. If you measure the spin of one electron, you instantly know the spin of the other electron, even if they're miles or even light years apart.
Wait, so they're like communicating with each other instantly. Doesn't that break the speed limit of the universe, the speed of light?
That's the catch. While it seems like they're communicating faster than light, they're not actually sending information.
So it's not like we can use entanglement to send messages across the galaxy faster than a speeding photon.
Exactly. The key is that entanglement is about correlation, not communication. Think of it like having two gloves, one right and one left. You put each glove in a box and send them to opposite ends of the universe. Now, if you open one box and find a right glove, you instantly know the other box contains the left glove. It's not that the gloves sent each other a message. It's just that they were always linked from the start.
Ah, so the information is already there. It's just a matter of revealing it.
Precisely. And this correlation holds true even for properties like spin.
So if we measure one entangled electron's spin as up, we instantly know the other one's spin is down, no matter how far apart they are.
Exactly. It's if they're performing a perfectly synchronized dance, even though there's no choreographer and no music.
Wow, that's pretty wild.
Mm.
So entanglement is more about knowing the state of one particle, allowing us to deduce the state of the other, rather than about sending signals between them faster than light.
You got it. It's a subtle but profound difference.
Okay, my brain is definitely starting to hurt a little bit. But before we push it over the edge, let's take a quick break. When we come back, we'll delve deeper into the fascinating world of entangled spin and how it's driving the development of some truly revolutionary technologies. Okay, so we've laid the groundwork for understanding this crazy thing called entanglement. But you mentioned earlier that it's not just theoretical.
No, not at all. In fact, it's actually being used to develop some truly mind-blowing technologies.
Mm, really? Like what?
Well, for starters, it's at the heart of quantum computing.
Quantum computing. That's like the holy grail of computing, right?
It's pretty darn
Hmm.
close. Quantum computers use entangled particles as qubits.
Qubits. Okay, another jargon word. What are those?
They're the quantum equivalent of bits, the basic unit of information in classical computers. But unlike a bit, which can only be a 0 or a 1, a qubit can be in a superposition of both states simultaneously.
Wait, so it can be both 0 and 1 at the same time?
Exactly. And that's where entanglement comes in. By entangling qubits, we can create these massive interconnected networks of quantum states that can perform calculations far beyond the reach of any classical computer.
So it's like instead of just having two gloves, a right and a left, we now have a whole room full of gloves, all entangled with each other.
Yeah, that's a good analogy. And the more entangled qubits we have, the more powerful the quantum computer becomes.
Wow. So quantum computing is basically harnessing the power of entanglement to solve problems that would take classical computers, even supercomputers, like forever to crack.
Exactly. We're talking about everything from drug discovery to material science to breaking the encryption that protects our online data.
Okay, so entanglement is basically the key to unlocking a whole new era of computing. But what about other applications? You mentioned something about quantum communication.
Yeah, that's another really exciting area. Entanglement can be used to create ultra-secure communication networks.
Ultra secure. How so?
Well, imagine you want to send a secret message to someone. You could use entangled particles to generate a shared encryption key.
A key that only you and the recipient know.
Precisely. And because of the weirdness of entanglement, if anyone tries to eavesdrop on your communication, they'll disrupt the entanglement, immediately alerting both you and the recipient that something's fishy.
So it's like a built-in alarm system that goes off if anyone tries to peek at your message.
Exactly. It's called quantum key distribution, and it has the potential to revolutionize cybersecurity. Because any attempt to intercept the key fundamentally changes the system. It's impossible to eavesdrop undetected.
Wow, that's incredible. So entanglement is not only driving advancements in computing, but it's also paving the way for a future where communication is virtually unhackable.
You got it. And those are just a couple of the many mind-blowing applications that are emerging from our understanding of this bizarre quantum phenomenon.
Okay, I think my brain is officially fried. We've covered a lot of ground today, from the fundamental weirdness of quantum spin to the mind-bending implications of entanglement.
We have. And we've only just scratched the surface of what's possible with this new quantum toolkit.
Mm.
But hey, we've got more deep dives to come, right?
Oh, absolutely. There's a whole universe of quantum mysteries out there just waiting to be explored. But for now, let's give our listeners a moment to digest all this quantum strangeness. Welcome back, everyone. I hope you've had a chance to process all the quantum weirdness we've been throwing at you.
Yeah, it's a lot to take in.
It is. But it's also incredibly exciting. So, as we wrap up this deep dive into quantum spin and entanglement, I wanted to touch on something you said earlier. You mentioned that these concepts aren't just theoretical, that they're actually being used to develop real-world technologies.
That's right. We're already seeing the impact of quantum mechanics in fields like medicine, navigation, and material science.
Can you give us some specific examples?
Sure. Take medical imaging, for instance. MRI machines use the principles of quantum mechanics to create detailed images of the inside of our bodies. And GPS systems rely on atomic clocks, which are incredibly precise timekeeping devices that use quantum mechanics to measure time based on the vibrations of atoms.
Wow, so quantum mechanics is already playing a pretty big role in our everyday lives. But
Yeah.
what about the future? What kind of technologies are on the horizon?
Well, as we discussed earlier, quantum computing has the potential to revolutionize everything from drug discovery to artificial intelligence. And quantum communication could lead to ultra-secure networks that are virtually impossible to hack.
It's pretty mind-blowing to think about the possibilities. But amidst all this excitement about technological advancement, I can't help but wonder about the philosophical implications of quantum mechanics. Like, if entanglement really allows for this instant connection between particles, does that mean our universe is fundamentally interconnected in a way we never imagined?
It's a profound question,
Yeah.
and one that physicists and philosophers are still grappling with. Entanglement certainly challenges our classical notions of space and time, suggesting that there might be a deeper level of reality where everything is connected.
Yeah, it's like if two particles can be linked across vast distances, maybe everything in the universe is ultimately connected in some way.
Exactly. It's a very holistic view of the universe, and it raises all sorts of interesting questions about the nature of reality itself.
Well, I think it's safe to say we've only just begun to scratch the surface of what quantum mechanics can teach us about the universe and our place in it.
Absolutely. And that's what makes this field so exciting. There's still so much to discover, so many mysteries to unravel.
Well, on that note, I think we'll wrap up this deep dive into the strange and wonderful world of quantum spin and entanglement. It's been a wild ride, but I hope you've all come away with a sense of awe and wonder at the sheer strangeness and beauty of the quantum realm. And who knows, maybe one day we'll be having another deep dive to discuss the even more mind-blowing discoveries that are sure to come.
I'll be looking forward to it.
Thanks for joining us.